Hello, friends. After a long time, I have got time to record another video for you all. And some of you have sent me comments and mails regarding restarting the sessions. So, thank you for your appreciation and concern. I am extremely busy these days with my research work and university works, so haven't found time lately. But I'll try to post some new videos on new topics. Today, I thought I should start off with the details of some important mineral groups. I had demands from some students who wanted these mineral groups because they are important questions in the GSI exam, and you all must be aware that the prelims of GSI has already been the results have been declared. So I think we should study some of the important mineral groups which uh, are asked in the GSI examination. So first of all, I shall be starting with olivine. Olivine is a nesosilicate, and you all are aware that nesosilicates, they are also known as island silicates. Island silicates. Why? Because they are simply isolated tetrahedra, isolated silica tetrahedra. The nesosilicates, they are also known as orthosilicates. Orthosilicates, they they consist of orthosilicate ion. So if you look at the orthosilicate ion, it looks somewhat like this. So it is the silica tetrahedra, means SiO4 4 minus. This is the orthosilicate ion. If you look at the structure of orthosilicate ion, we have silicon in the center, and it is bonded to 4 oxygen atoms with 4 minus charge. Now the bond angle between silicon and oxygen here, this is 109.5 degrees, and this bond length from silicon to oxygen, it is around 162 picometer. With this background of nesosilicates, let us now move ahead to our first mineral of today, that is olivine. Olivine, we all know, is a very important mineral. It it is the first mineral to crystallize in the Bowen's reaction series. So we all know that in the Bowen's reaction series, there are two series, the continuous series and the discontinuous series. And olivine is the first mineral to form in the discontinuous series. So it is a very important mineral. If you look at this olivine system actually, so olivine group, it consists of an isomorphous series of nesosilicates. So they have similar kind of crystal structure. Its general formula is R2 plus SiO4, where R, so, this should be capital R, sorry, R is either magnesium ion or iron, Fe2 plus or Mg2 plus. So this these are the two end members, of the olivine. The Foster Mg bearing member is fosterite with the chemical composition of Mg2SiO4, while phyllite is the iron bearing member, Fe2SiO4. If you look at this plot over here, this is called as a solid solution series. You all must be aware of the solid solution series in your mineralogy as well as your igneous petrology classes. So not much to deal with here, but here we can see a very important thing. That is, we have the um, liquid phase, that is the melt. Then we have the olivine solid solution over here, while in the central part we have the olivine solid solution, that is olivine plus liquid. And forsterite forsterite forms first, while phyolite is formed later. This question has been asked several times in the past, that why Mg bearing olivine or forsterite forms earlier than the Fe bearing olivine or phyolite. So we will discuss this question as well in the coming slides. So if you look at this first figure over here, this is forsterite, then this is phyolite, this is Larnite. So what is Larnite? Larnite is calcium bearing olivine. So there are limited solid solutions uh, between the olivine forms. So if it is Ca2SiO4, it is Larnite. If it is Mn2SiO4, it is tephroid. Tephroid. Then we have monticelite where CaMgSiO4. So looking at this plot over here, one thing is very clear, that the temperature of melting, if suppose that we have olivine, solid solution series, and we start heating it, so as we reach at the temperature of 1205 degrees Celsius, then theoretically, from that solid solution, the firelight, that is iron bearing olivine, will melt first, and then we keep on increasing the temperature at 1890 degrees Celsius. It is the melting temperature of forsterite. So if we reverse it, that once the minerals are being crystallized from the melt, and melt is at a temperature, let us say T, where T is more than 1890 degrees Celsius, which means that now at the temperature T, both forsterite as well as firelight will be in melt phase. Now, as the magma chamber starts to rise, means the temperature starts to decrease. As the temperature reaches 1890 degrees Celsius, the forsterite will start to crystallize, because 1890 is the melting point of the forsterite. So as the temperature of the melt decreases further, means it becomes lower than 1890, the forsterite olivine or Mg rich olivine, it will come out of the melt in solid form. Further, as the magma chamber continues to rise, then the temperature will keep on dropping, and as soon as the temperature reaches 1205 degrees Celsius, firelight crystallizes out of the system. This is what this means. Now let us look at the olivine structure. In the very beginning, I said that olivine, it is uh, a nesosilicate, which means that the olivine has scattered, or isolated silica tetrahedron. Olivine belongs to orthorhombic system. Orthorhombic system. So in olivine, the structure of olivine consists of individual silicon oxygen tetrahedra, which are linked by MgFe atoms, each of which has 6 nearest oxygen neighbors. So it is, if you look at these triangular diagrams, they represent the silicon oxygen tetrahedra, and these tetrahedra are linked by either Mg or Fe. And this MgFe, they are arranged in such a way that each of them has 6 nearest oxygen. So in this figure, the smaller white and black circles, they represent oxygen. So this is oxygen. Okay, this is also oxygen. So I have not shown silica or silicon atom in this diagram. So let us now understand. If you look at the arrangement of silicon oxygen tetrahedra, there are two ways in which they can be arranged. One way is that in this case, let us call it A, and call this as B. So the tetrahedra A is pointing downwards. Okay, it is pointing downwards, while tetrahedra B is pointing upwards. So here you can see that these two tetrahedra are arranged in such a way that their bases are parallel to each other. Okay, so you can see that this space here, it is arranged parallel. In between this, the bases of these two tetrahedra, there is a site which is called as M1 site. M1 site is smaller in size and it is occupied by Mg2 plus. We all know that the ionic radius of Fe2 plus is more than that of Mg2 plus. Why? Because the atomic radius of Fe is more than Mg. The simple reason is that if you look at the electronic configuration of iron Fe, it has one extra valence shell that makes its radius more than that of Mg. And let me just remind you here that it is because of this only, it is because of the smaller radius of Mg2 plus that Mg2 plus is well bonded, or it is strongly bonded as compared to the Fe2 plus. Means the bond strength of phosphorite is more as compared to phyllite, and therefore the phosphorite bonds, they need more energy to be broken, and this is the reason why the uh, phosphorite has a higher melting point, and therefore phosphorite, because it is consisting of Mg2 plus, which is a smaller ion, then it forms first in the Bowen's reaction series. So here, if we look at the first column where the tetrahedra are arranged in such a way that their bases are parallel to each other, we see M1 site. And M1 site is the smaller site which is occupied by Mg2 plus. Now, look at the second column in which the, let us call it tetrahedra C and tetrahedra D. Now, here they are arranged in such a way that the base of tetrahedra A is facing the tip of the tetrahedra C. Similarly, the tip of tetrahedra B is facing the base of tetrahedra D, which means that here, this space which is available, this space is larger space, means it has the ability to house larger ions, that is Fe2 plus. So this site, it is called as the M2 site. It is larger in size and it is occupied by Fe2 plus, that is the ferrous ion. So as earlier I was saying that the oxygen atoms, they are arranged in a hexagonal array. Why? Because here in this case, the cations or the Mg and Fe2 plus, they are surrounded by six neighboring oxygen atoms. Okay, six nearest oxygen neighbors. So if we look at this setup, so it's very easy that you draw two tetrahedra with their bases parallel, while the tip of one tetrahedra will face the base of other tetrahedra. So if we try to check this out, the hexagonal array, see here, 1, 2, 3, 4, 5, and 6. So see, you found that there is this hexagonal array of the oxygen uh, in the tetrahedra. So here the structure consists of isolated tetrahedra in which the corner oxygen form the octahedral groups. Because it is hexagonal, so you know that if you look at the coordination number and the associated geometry, number 6 is associated with octahedron form, octahedron shape. So here, in case of olivine, the M1 and M2, they both are octahedral sites. M1 and M2, they both are octahedral sites, and these octahedral sites, they are housed by the smaller one by Mg2 plus and the larger one by Fe2 plus. And remember that this hexagonal array will not be a perfect hexagonal, it will be a distorted octahedron. Okay, so here what did we see? We saw that in case of olivine structure, the isolated tetrahedra are arranged in two ways. For the formation of a smaller M1 site, we have the tetrahedra arranged in such a way that their bases are parallel. While in case of larger M2 site, they are located in the location where tip of one, yeah, corner of one tetrahedra is facing the base of another tetrahedra. Okay, so this is the reason that M2 sites, they are larger than the M1 site because they get more space to be formed. Now let us look at the larger picture of the olivine structure parallel to 001 plane. So once we look at the 001 plane, what does this mean? It means that if we, this is an orthorhombic system in which all the three axes are perpendicular to each other, but they are not equal to each other. So A is not equal to B, is not equal to C, but alpha, beta and gamma, all three angles are 90 degree. So if you look at this plane parallel to 001, it means that we are looking it in at the structure in such a way that the surface is it being intersected by C axis while it is running parallel to A and B axis. So if you look from the top, so this is C, this is A and this is B. So if you look from the top, you will see such a structure. Now this structure might seem very complex to you, but take my words, if you are able to draw this structure in the GSI written examination, I can guarantee you that you will get full marks for it, because it looks like it is very complex, but it is actually not. So its concept is from this diagram. Here you see that the location of M1 site is where the bases of two tetrahedra are parallel. Now see this. We have the M1 site here, which is the smaller one, M1, M1 side. So here this M1 side is located between, this is one tetrahedron, let us mark it as 1, and this tetrahedra over here, it is running parallel to the base of this tetrahedra, which we mark as 2. So between the bases of two tetrahedra, what do we get? We get the M1 side. Similarly, this is 1 and then this is another. So you can see that the bases are running parallel to each other. But what about the M2? M2 site is located where the tip of one tetrahedra is facing the base of another tetrahedra. So here you can see that this triangle which is shown over here, this triangle which is incomplete, it is this could have been the tip of one tetrahedra, but it is facing the base of this tetrahedra, where which is marked by silicon. So to draw this, what you need to do is very simple. Just try to remember it rather than making it more complex. First of all, draw three tetrahedra, these three triangles. Very simple. Very, don't try to make it very big in the examination. So these three tetrahedra, they are drawn. Remember that these will be the M1 sides. Draw the tetrahedra like this. this way, this way. Now, then again draw three tetrahedra, three triangles here, like this. Okay. Then join this one, and then this represents an octahedron site. This way. Just follow this video how I am drawing these. Okay. And this is not, this is, they are opposite to each other, they are facing opposite. This is also M2, sorry, this will be M1, M1, M1. This is M2, M2, and then simply add it. So we got the M1 as well as M2, and then simply just draw one tetrahedra here, this way, and this way. Even if you stop over here, I am telling you that you will get full marks for this diagram. Okay, so here this is, again this is, I forgot to, this is M1 again. So we have, if so, in accordance with the orthorhombic symmetry of the silicon oxygen tetrahedra, they point alternately either way along each of the x-axis and y-axis, x and y directions. So one tetrahedra will be facing upright. See, the second tetrahedra will be facing down. This is how this structure looks like. So as I had told you that the Mg2 plus and Fe2 plus ions, they both are distributed in the M1 and M2 sites respectively. So if we write it over here, this site will specifically be Mg2 plus and this site will be Fe2 plus. And you can see here with the help of this diagram only that M1 site is smaller and M2 site is larger. All right. So if we look at the olivines, they vary in composition from Mg2SiO4 to Fe2SiO4. There is a complete diadochi between the Mg2 plus and Fe2 plus ions. Now, what is diadochi? Uh, it is the phenomenon of complete replacement of one ion by the other. So Mg in olivines, you can have Mg2 SiO4 which can be completely replaced by Fe2 to Fe2 plus to make firelight or Fe2 SiO4. Now, in general notation, olivines can be written as FO 100 to 90, means that olivines, they consist of forsterite 90 to 100%. What does this mean? FO 90 to 100 means that it is only Mg2 plus SiO4. Now, if Mg2 plus S, because it is a solid solution series, so Mg2 plus SiO4, uh, this composition should be either 90% or 100%, from 90 to 100% to call it forsterite. But if this composition is 10 to 0, what does it mean? That it is the Mg2 2 plus SiO4 content is, it ranges between 10% to 0, means here now Fe2 plus component is 90 to 100, only then this will be called as a firelight. So what is the definition of forsterite and firelight? Forced olivine will be named forsterite when it has the forsterite content Mg2 plus content 90 to 100%, and it will be called as firelight only when it has Fe2 plus content 90 to 100. Now, it has been seen that in more Fe-rich olivines, there is little replacement of Mg and Fe by Mn and Ca. So, I had told you that Mn is tephroid, Ca is larnite. So, this you may also remember that larnite and tephroid are also the type of olivines where there is little replacement of Mg by Mn and Ca. While in case of mg-rich olivines, nickel and chromium are no commonly present. Okay, all right. So the melting point of forsterite is 1890 degrees Celsius. It increases with pressure under anhydrous condition and decreases with pressure under water saturated condition. What does it mean? That if you, let us just first draw it. See, all these topics which I am discussing, they are actually answer to one full question. So, if in your mineralogy paper, this question is asked, say, for example, discuss in detail the structure, composition, physical properties, association, and paragenesis of olivine. So, this is all what you need to write, which I am discussing in this video. Now, let us look at this statement. This is the temperature. Yeah, this is temperature in degrees Celsius, and here it is pressure. Sorry. So this is pressure in kilo bar. Okay. So what is the statement say? The statement says that melting point of forsterite is 1890 degrees Celsius. It increases with pressure under anhydrous conditions. Means it is now dry conditions. There is no water or uh, no liquid over there. So if we bring olivine in the anhydrous conditions, then the melting point of forsterite will be more than 1890 degrees Celsius. So this is anhydrous condition. This will be liquid forsterite. While it is saying it decreases with pressure under water saturated conditions. So if now we introduce water in the system, then the melting point of forsterite will decrease with pressure. So here it will be liquid plus vapor, and then forsterite plus vapor. Okay, so this tells us that the behavior of the olivine changes once the system is having water or it is anhydrous with varying pressure conditions. So the thermal behavior of Mg solid solution series, it explains the effect on melting temperature in a diadochic series of replacing a smaller ion by a larger. What does this mean? That here the ionic radius of Fe2 plus is more than Mg2 plus. So what happens here if we apply the concept of diadochism, where the smaller ion is being replaced by the larger ion, then here what will happen? The thermal behavior will change. Why does this happen? So for the larger ion which is Fe2 plus, the uh, cation anion bonds are weaker. Cation anion bonds are weaker. Okay, so as the number of larger cations in the structure increases, there is a progressive reduction in the melting point of the intermediate composition. So for example, we have this composition as FO, let us say 60, and FA, let us say 40. So definitely this is an intermediate composition, and the melting point will definitely be now lower than in the case of FO 90 to 100. Why? Because a firelight, which is now constituting 40% of the solid solution series, it has more number of what do we say, Fe2 plus ions, and therefore as a result the bond strength, it will become weaker, and the temperature will keep on going down. So the first olivines to separate from a liquid of given composition, they are rich in Mg2 plus, and consequently larger Fe2 plus are rich in the residual melt. This is the reason for the higher abundance of forsterite than phyllite in the natural systems. Let me add one slide here. So what I was trying to say, that as I had been discussing with you since the beginning, that the forsterite olivine, it forms first from the melt. And also remember that forsterite is the uh, 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 it is the most abundant olivine, or it has higher abundance than firelight. Why? Because let us say we have a melt. This melt consists of forsterite plus firelight, and this melt here right now is at temperature T1. Now this magma chamber or this melt, once it's rising and its temperature goes down to T2, where T2 is less than T1, and suppose that this T2 is actually 1890 degrees Celsius. Now what will happen in the magma chamber? The olivine will, sorry, the forsterite will solidify. This will be forsterite, while in the residual melt, what will remain? It will be firelight. So the this is the reason that the first event of formation of forsterite makes it uh, abundant than firelight in the natural systems. Now olivine is very susceptible to hydrothermal alteration, weathering, and low grade metamorphism as well. So there is the reverse of this Bowman's reaction series, which is called as the stability series. So what does stability series say? First to form, first to weather. So olivine, if it is contained in any rock, it is more likely to be altered or weathered than any other mineral. So the rock consisting entirely of olivine, it is called as dunite, almost 90 to 100% olivine. But this rock is very unstable, because olivines, they are susceptible to hydrothermal alteration, weathering, low grade metamorphism. Okay, now what happens here? The alteration, it involves the diffusion of hydrogen ion into olivine structure, where they temporarily get attached to oxygen ion, release magnesium, Fe, and silicon ion from their sides. So what happens over here? What does alteration do? Alteration, what does it do? Alteration involves the diffusion. So H plus diffuses into the olivine structure. Diffuses into the olivine structure. What does it do then? It attaches to the H plus attaches to oxygens, corner oxygens, and releases Mg2 plus, Fe2 plus, and silicon ions from the sides. So now what happens? The same olivine, it now gets replaced by Fe3 plus, Fe3 plus, aluminum, and calcium. So this is how the olivine structures gets altered. So the most common form of alteration of olivine, the most common form of alteration of olivine is called as serpentinization. Serpentinization. So as the name suggests, here the product will be serpentine. So the serpentinization is a very common process in the rocks like dunite and peridotite. So serpentinization occurs very commonly, as I have just told you about dunite, peridotite. These are the rocks which consist of olivine in large amounts, and they get completely altered or weathered. So what is the process or the reaction that happens over here? Say we have, sorry, we have phosphorite Mg2SiO4, and then now the water comes in. Okay, let me just balance it as well over here. So it becomes now Mg3 Si2O5 OH4. Then we have MgOH2. So this is serpentine. This is serpentine, and this is the brucite. So you saw that the olivine, so and this is forsterite. Forsterite got altered to serpentine and brucite. So the alteration products, they occur as three polymorphs of serpentine lizardite, chrysotile, and anticorite. So you should remember these names. They can be asked that what are the polymorphs of the alteration products. So the alteration products, the alteration products, they are the polymorphs of serpentine lizardite, then chrysotile, and anticorite. It will be good if you remember their composition. If not, then not a big deal. So it's not easy to remember the composition of all these minerals. Okay. Now let us look at the physical properties of olivine. So as I indicated earlier in this lecture also, that the crystal system is orthorhombic. Then olivine, it occurs in form of prismatic crystals which are modified by domes and pyramids. They can be massive or compact. Okay, so the prismatic crystals are the common ones. Just like any orthorhombic mineral, the olivines, they have prismatic crystals, and they are modified by domes and pyramids. So I'll just show you over here. Then color, the color is green, pale green, olive green. The name Olivine has come from the olive green color. White, yellow, brown, black. Peridot is the gem variety. Remember that. Peridot, it is the gem variety of Olivine. Uh, Streak is colorless, hardness around 7, vitreous luster, and now since it has vitreous luster, the fracture is ought to be conchoidal. So if we look at these two crystals of forsterite and phyllite over here, you can see the marked difference in their shapes, in their habits. So if you look at the forsterite crystal, how is a prism defined? Okay, how is a prism defined? So let me just draw for you a simple prism. This is the diagram of a, if you follow my previous crystallography lectures, you will see all these over there. So prism is defined as the crystal form which runs parallel to the c-axis and it intersects the a and b axis. So if we assume that all the faces are being intersected by the axis at unit distance, then prism should be 1 1 0. So the first order prism. If you look at the second order prism, so there the axis pass through the faces, center of the faces rather than the solid angles. So it will be 100 like that. So if we look at these two pictures over here, now what I said in the beginning, that it is prismatic crystals, but they are modified by modified by domes and pyramids. So for example, in this over here, this this particular face, this one, which is 001, here the c-axis is intersecting. So remember, prism is always an open form, and prisms, the normal prism, they are closed by pinacoid faces, the basal pinacoid. So here, this particular face, it is the basal pinacoid. Basal pinacoid. Now, because it is intersecting the c-axis and is running parallel to A and B. If you look at this 0 to 1, what does this suggest? That it is the 0 to 1 phase. It is running parallel to the a-axis and it is now intersecting the b-axis at half the unit distance and c-axis at double the unit distance. So if we convert it like that, it becomes 0 to 1. But what is this phase? What is 0 to 1? 0 to 1 is the dome phase. How is the dome defined? If you go to my previous lectures, there I have told that dome faces are just like prism only. They are open forms, but there the c-axis will definitely be intersected and either of A or B will be running parallel. Now, if you look at this phase 010, it is again a pinacoid, but it is the B pinacoid over here. Now, if you look at this particular phase, 110, it is a typical prismatic phase. And 101, this phase, it is again a dome phase. This is a dome, this is again a pinacoid, and this is a prism phase. So prima facie, we saw that forsterite has a prism which is modified by several other type of forms like basal pinacoid, B pinacoid, domes, etc. Similarly, if you look at the phyllite again, this phase is a pinacoid phase. This is again the pinacoid phase, while 0 to 1, it is a dome phase. 101, it is again a dome face, and 110, it is a prism face. So here you saw that the crystals which you can see, they are showing a modification of the crystal form. Now again, my advice, try to learn how to draw these crystal diagrams. Even if you forget some of the Miller indices, but you know that this is a dome face or this is a prism face, then take my word, you are going to get full marks for this question. Now, the olivines, they the olivines of metamorphic origin, they occur principally in the rocks of ultramafic composition, in impure carbonates and in iron rich. So we know that the olivines, they are one of the important minerals of the igneous rocks, and they are first to form in the Bond's reaction series. But the olivines, they are also metamorphic in origin. So the olivines of metamorphic origin, they occur principally. So olivine of metamorphic origin, where does it occur? It occurs in rocks of ultramafic composition. It occurs in impure carbonates. It occurs in iron rich sediments. Okay. Most of these olivines are highly rich either in forsterite or phyllite. Now, as we had been talking about the alteration of olivine to serpentines, so the progressive metamorphism of serpentinites, it causes the most extensive development of olivine. So let me add a few more slides over here so that I don't have to skip it again and again. All right. So what I was saying is that the progressive metamorphism of serpentinites. Serpentinite is a rock, right? Progressive metamorphism of serpentinite. What, what does it cause? It causes the most extensive development of olivines. So let us write a balanced reaction over here. 5Mg3O5OH4 plus. So this is serpentine. I'll write later. Now CaMgSi2O6. What is this? This is diopside. Now 6Mg2SiO4. Don't bother with the balancing of the reactions, just write the reactions correctly. Even if you don't remember the chemical composition properly, I'll write the names of the minerals. Just remember those. They are more than enough to get you fetch you good marks. Ca2 Mg5 Si8 O22. I know that it is not easy for you to remember all the formula. Even I don't remember all the formulae, but since I am writing this here, I have written these compositions in front of me on a piece of paper, so I can write it easily. Now, so what is it? All the minerals. So serpentine reacts with or undergoes progressive metamorphism, combines with diopside to give forsterite, tremolite, and water. So the equilibrium temperature of this reaction, equilibrium temperature, it is around 485 degrees Celsius, and the partial pressure of water over here is same as the total partial pressure, which is equal to 2 kilobar. So what does this mean? That at a temperature of around 485 degrees Celsius and a partial pressure and a pressure or total pressure of 2 kilobar, the serpentine reacts with diopside to give forsterite and tremolite. Similarly, if you look at another reaction, so uh, serpentine, it gives rise to forsterite. It breaks down to forsterite, forsterite talc, etc. So Rather than bothering you with the formula, I'll simply write the names of the minerals. Serpentine is a reversible reaction. It may give rise to forsterite plus talc plus. Then another reaction where serpentine may react with brucite MgOH2 to give forsterite plus water. So what does this mean? That the progressive metamorphism of serpentines, they may give rise to forsterites. Now the last part is the paragenesis. Very important thing in all the questions regarding the details of the minerals or mineral groups, paragenesis has to be written over there. So olivine is a major constituent of dunite, monomineralic rock, and peridotite. Peridotite. It varies in composition between forsterite 96 to forsterite 87. Of course, as I have told, forsterite 96 to forsterite 87. So this is the variation in the composition of olivine. As I have told you earlier also that FO olivines, that is forsterite olivines, are most abundant. Now, in some larzolite, the composition gets progressively richer in iron with forsterite composition of FO82. Which rocks? Laherzolite, LHERZO. I'll show you a diagram of the paragenesis also. Laherzolite. So what happens here? That the composition gets progressively richer in iron and Fe, that is iron, uh, and the composition now changes from FO87 to FO forsterite 82. Then you also get olivines in ultramafic nodules in basalts and kimberlites. Kimberlites. So here, in case of ultramafic nodules in basalts and kimberlites, the composition now it ranges from FO91 to FO86. Again, more rich in the forsterite. But now, if we look at the gabbroic rocks, in gabbroic rocks, the compositional range of olivine is between forsterite 80 to forsterite 50. Means now the olivines are getting richer in the iron content. Okay. So the olivines, they occur in a wide variety of volcanic rocks. Olivines occur in a wide variety of volcanic rocks. Now, how they occur as both ground mass as well as phenocryst. So this is the crystal habit of olivine in the volcanic rocks. Then most magnesium rich olivines, uh, composition of FO94 to FO85, they occur very commonly in ultramafic komatiite lavas, ultra basic komatiite lavas. They are very commonly found over here. While the Fe-rich olivines, they occur in both alkaline and acidic plutonic and hypabyzal rocks. Okay. Now, As I had told you previously that they also occur in impure carbonates. So in metamorphosed impure carbonates under anhydrous conditions. These things are very, very important. Those of you who have read chemistry in their lower classes, they know that hydrous reactions are different than anhydrous reactions. So, how is this represented as? So it will be CaMgCO3 whole. So this is the impure carbonate or dolomite plus silica will give rise to Mg2SiO4 plus 2CaCO3 plus 2CO2. Okay, so it means that the impure carbonates, once they get metamorphosed under anhydrous conditions, they also have this phosphorite in their composition. Now, in case it becomes hydrous conditions, okay, so in case of hydrous condition, what happens? In case of more hydrous condition, tremolite is a product of metamorphism. So now, and so this is the anhydrous condition. Under hydrous conditions, what happens? The reaction between tremolite and dolomite, it gives olivine as the product. So Ca2 Mg5 Si8 O22 OH2 plus 11 CaMgCO3 whole twice, it gives rise to 8 Mg2SiO4 plus 13 CaCO3 plus 9 CO2 plus H2. This is how the tremolite reacts with dolomite to give phosphorite. Phyolite also occurs in metamorphosed rocks, but in medium grained, thermally metamorphosed, iron rich sediments and in rocks of more cherty composition. Cherty composition now here, uh, 2FeCO3 plus SiO2 will give rise to Fe2SiO4 plus 2 CO2. Sorry, CO2. So here the Fe-rich sediments, they react with silica to give rise to light. Okay, so now let us look at the diagram of the paragenesis. So if you look at the paragenesis here, we have the olivine, orthopyroxenes and clinopyroxenes, and the there is a very fine distinction between peridotite and pyroxenite. So here we have these rocks. If it is a monomineralic uh, olivine bearing rock, we call it as a dunite. If it is orthopyroxene, we call it orthopyroxenite and clinopyroxenite. Now orthopyroxene clinopyroxene series, it has websterite, and then olivine orthopyroxene is harzbergite, olivine clinopyroxene is wurlite. Now, laherzolite, as I had told you, that the laherzolite, in case of laherzolite, the iron composition gets progressively richer, and wurlite, as I had told you, it is a rock formed by the it's the series between olivine and clinopyroxene. So this is all about the paragenesis of olivines, and I am sure if you go through this video and you make your notes properly, you will be easily able to understand the olivine part. Important thing over here is the important thing over here is the structure, which I had told you in the beginning. This is something which is very appealing, and you should practice this diagram as I had told you by making the triangles and the associated structures. So I hope you have understood this, and do try to make these diagrams. Try practicing the Miller indices and send me the questions if you have any on this topic. Bye bye. See you very soon with the next videos.